Hi, my name is Trevor Arndt. This is my lab report for the third lab. Here's my introduction. The goal of this lab was to examine and predict the behavior of basic currents, and we did this by creating currents in an online current software. The results that I found from this lab was that current is always conserved in a circuit, and the resistance times the capacitance of our last circuit was equal to 5.86 ohms times farads, which was very close to the expected 6 ohms times farads. The physics concepts that you need to know for this lab are circuits, and I've included an example of resistors in series and parallels to show the two different types of orientations that we used in this lab, where resistors in series are when they're in a line, resistors in parallels when they run alongside each other. You also have to know what current is, which is the flow of electricity or electrons through a loop. You have to know the loop rule, which states that the change in electric potential, well, the sum of the change in electric potential is equal to 0 for a circuit, and that proves conservation of current. You have to know what resistors and capacitors are. Resistors resist the flow of current in a circuit, and capacitors store electricity in a current. The models that we used in this lab included the round trip potential plot, which we used to show the loop rule, and the change in voltage versus time graph, which we used to create a line of best fit from which we could find the R times C, which was our final result. Here's the process. We built a circuit with two resistors totaling 147 ohm, two 1.5 volt batteries, and an ammeter. We used the voltmeter to test the potential difference at every connection point around the circuit. And then we added those potential differences together according to the loop rule, and the result was found to be 0. The second part was we built another circuit with a 30 ohm light bulb, a 9.9 volt battery, and a 30 millifarad capacitor. We charged the capacitor, and then we released the charge in the capacitor and observed the potential difference, or the difference in potential across the capacitor for 20 seconds, recording it at different points. And then we created a graph with those results. Here are my experimental findings. For the first part, I found the potential difference to be 0 across the circuit. The potential started at 3 volts and then decreased across the two resistors back to 0. The second part, I found after plotting the graph with the natural log of delta V over V naught versus time, I got a negative linear slope. And after manipulating this line of best fit according to the formula below, I found R times C, which is the resistance times the capacitance, to be 5.86 ohms times farads. And the reason this is different than the expected 6 ohms times farads is probably because of the way that I found this result, where I just took the line of best fit for my findings, and then I manipulated them according to this equation below, so the result was not exact. Here are the models that I created, and the model on the left is my delta V versus time graph, and I've included the raw data below. And then I completed this graph on the right to show the loop rule. My conclusions. If we were doing this lab in real life, we used an actual ammeter instead of an ideal simulated ammeter. The difference would be that in real life, the ammeter would have resistance as opposed to the ideal 0 resistance in the simulation. And this increased resistance would have decreased the amount of current at certain points, giving us below expected results. And if we were to do this lab in real life and we used a real battery to charge a real capacitor with no resistor in the circuit, our model would predict the capacitor would be charged instantly due to the lack of resistance. However, in real life, the battery and wires would have some amount of resistance, so the capacitor would take some amount of time to charge. For this lab, I guess I should include this, but our system would be the circuit. and the surroundings would be everything else. And because we are using an online circuit generator, there would be no interference from the surroundings. So our results would be ideal, as opposed to in real life where there would be multiple factors that would mess with these, mess with the results, including the resistance. And I've kind of gone over that in the conclusion, but thank you for listening.